Everyone, Mr. Smith here, and in this video lesson, we are going to discuss the domain and range of a function. So what does the domain of a function mean? What does the range of a function mean? So let's get started. So for any relation, the set of values, so for any relation or function, the set of values that can go into the function or relation is called the domain. So if you recall, we've had this discussion, and I finished off our last lesson with this. But, and you don't need to write this down, but I'm just writing it down as a talking point. But remember the function y equals root x? There were certain x values that you couldn't plug into that. It would kind of break the function down. So if you think of a function as a machine where you input an x value and you output a y value, certain values break it. And the values that you are allowed to put in, that's what we call the domain. The domain of a function is just the x values that you're allowed to put in, that's all. And the range is the y values that come out. So every function is like a machine. You can put in certain x values and you get out certain y values. And what we would like to do is today get some experience looking at some functions and thinking about what am I allowed to plug in and what kind of numbers will come out. We're also going to review some mathematical language that will help us make describing those sets of numbers easier. Now, for a function, so we know that a function, one x value produces one y value. There's no points stacked on top of each other. So with a function, if you put in an x value, you get out one specific y value. But for some relations, when you put in an x value, you might get multiple y values, but not a function. There's a one-to-one correspondence there. Let's just dive in. We're going to look at a lot of examples today, guys, talking about the domain and range, also talking about, well, like looking at these relations, talking about domain and range, and then thinking, okay, are these relations functions or are they not? So here I've given you a relation, and in this particular one, I've just given you the set of points. Like this is the relation, these 5 points. If you could take these 5 points and make a graph if you wanted to. So let's talk first about the domain. So in situations like this, where you're actually just given the points, the domain is really easy to write out. So when we're describing the domain, it's often a set of numbers. And when we're describing a set of numbers, we use special brackets. We use these curly Q brackets. Now, being a math teacher, I have lots of experience making curly Q brackets. You might not, so yours might just look like little squiggles, but you'll get better over time. So what are the x values of this relation? Well, we have, and it doesn't have to be in order for sure, but we have -3, 5, -2, 5 again. I don't need to write 5 again. 5 is there already. And 6. So that's the domain of this relation. What's the range? So what y values come out? Well, let's list the y values. 4, -6, 7, 3, and -8. So our first example, listing domain and range, we listed the x values, we listed the y values. We just listed them. There was only a few of them, so it wasn't a big deal. We just wrote them as a list. Now I'll ask you, is that relation a function or not? And maybe as a hint, I will say, can you visualize what the graph would look like, or even make a rough sketch yourself? I'll wait a second while you do that. Hopefully you said that this relation is not a function. Why is it not a function? Because the problem is x equals 5. x equals 5 has 2 y values, and those points would be stacked on top of each other. So this particular relation is not a function. Why? Because 2 of those points are above each other, and it would fail a vertical line test. So again, we're getting lots of practice right now, just getting experience, stating domain and range, and then also tying in our function or not. Here's another example. So this is, in this particular problem, it's a lot like A, where you're just given all the points. Here it's in a table form. And in this case, instead of X and Y, it's a dependent variable and an independent variable. Here, the number of children in a camp depends on what age the children are. So you can see that there's less kids in the younger ages. So let's write out the domain and range. So the domain, again, it's pretty easy for us just to list the numbers: 4, 5, 6, 7, 8, 9, 10. If you can list them easily, then just list them. The range, what values do we get for the dependent variable? If you want to just even add an X and Y here to help you, that's totally fine. Just list them. So we have 8. It doesn't need to be in order. It's okay. If you're that type of person that needs them in order, then by all means, you put them in order. 8, 12, 5, 22, 14, 9, and 11. And there were no repeats. So I'll ask you guys, is this relation a function or not? And hopefully you said, yes, it is a function. Every X value here corresponds to one Y value. If you were to graph these points, none of them would be over top of each other and it would pass a vertical line test. So yes, this is a function. Let's continue. So in those two examples, you were just given a set of points. And it was easy for us to just list the domain and range because we just write down a few numbers. When the equation of a relation is given, the domain and range, we just can't write down certain numbers. So I think all of us understand that the graph y equals negative x plus 3 is going to be a linear relation. And there's just no way to write down every single x value. So let's actually dive in and see what I mean by that. So this graph, we can draw it by hand. So this is the line that has a y-intercept of 3, and its slope is -1. So from there, down 1, right 1, down 1, right 1. So after grade 9 and 10, we've all seen linear relations quite a bit, or a linear function in this case. That's what it looks like. And if we look at that graph, that graph hits every single x value. If you think about what kind of things are you allowed to plug into this equation, well, you just can't list certain numbers because it's basically every number. So how can we write that down? What kind of notation can we use where we can't list all the numbers? We have a large range of numbers. So that's what we're going to be getting into next. So I'm going to describe this in words right now. The domain for this function is x can be any real number. Now, it'd be nice if we had a math way of saying that, and we do. So here is the math notation. And so I'm going to just use a different color here. Here's how we write this. We use set notation, so curly Q brackets for the domain. And if we want to say x can be any real number, we say this. We say x, and then this is a little funny e. This is the Greek letter epsilon. And then we write an r. And so what this is saying is x is an element of the real numbers. And it is just a nice, compact, concise way of describing a large set of numbers. And it's going to be expected of us moving forward in later grades, if you take math in university, that we start using this set notation. And I find that reasonable. I mean, we're taking the functions course. We're choosing to take the highest level of math, high school math. We got to get used to, using this kind of formal language. So we can say in words, x can be any real number, but our mathematical notation will be this. Set notation, x is an element of the real numbers. What kind of y values come out of this equation? So I know that I can plug in any value for x. It doesn't break this equation. It's a pretty simple equation. But what kind of y values to come out? Well, if you look at the graph, you can see that the graph is going to keep going up, and it's going to keep going down, and it's going to hit all the y values too. So for the range, we can say something similar. We can say that the range for this particular function is y can be any real number. So that's our first example of using some new notation. So it might take some getting used to, but we can do it. I personally would rather write down my set notation than have to keep writing in words over and over again. X can be a number. X can be any real number. I'd rather use set notation. All right, let's look at another example here. So maybe this looks familiar to you. We are going to review some quadratic functions over the next few days. It's my hope after your grade 10 course that you could actually graph this one by hand. But let's graph it together in review. So if you recall, this was the vertex form of a quadratic relation. In this case, it is a function. And the vertex of the parabola can be found by looking at what number is beside the x and what number is outside the squared. And if you recall from grade 10, it turns out the vertex is the opposite of this number for the x value. And the y value is actually just the number on the end. So the vertex for this guy is 1, 3. And the step pattern, because there's no number out front stretching it, the step pattern is the same as the basic parabola. It's 1, 3, 5. So to sketch this guy, we put our vertex at 1, 3. So I would expect everybody to be able to pick off the vertex. If you didn't get the step patterns, because depending on your teacher, you don't do step patterns or do them a different way. Everybody should be able to say, okay, it's 1, 3 is the vertex and it opens up, but we can add a bit more detail because the step pattern is up 1 and then up 3, and same on the other side. So we can add a bit more detail. But there's the graph. Now, guys, having made the graph, we can now state the domain and range. So look at the graph, guys, or look at the equation. What x values are you allowed to plug in to that equation? Are there any x values you could plug in that would give you an error or kind of break the function? And the answer is no. And if you look at the graph, parabolas keep going forever in either direction. They hit all the x values. So the domain here for this quadratic function is x can be any real number. But do the y values hit any real number? Does this graph go forever up and forever down, touching all the y values? Or does it only hit a certain range of y values? So maybe in words, can you see what y values this parabola hits? And you can just pause the video or just, if you would like to think for a moment. Because look at this parabola. This parabola only hits y values that are above or equal to 3. It never goes below 3, right? So how can we write that with some set notation? So this is a new, I'm going to write this in words first. So y is greater than or equal to 3. And that's perfect for the range. We've described the range in words. That parabola, the y values that we get when we plug it in the equation, we only get y values 3 and above, and you can see that from the graph. But how can we turn that into a nice, concise, compact mathematical notation? So here's how we do it. We use our set notation, curly Q brackets, and we say that y can be any real number, so like that. But now we have a condition. Y just can't be any real number. It's greater than or equal to 3. So you can use a comma, which is fine. I'll use a comma here. So we say additionally, y is greater than or equal to 3. And that's how we'll say that in words. And again, we'd like to progress where we all can use this set notation. But for now, we'll put things in words when they're new, and I'll show you how to put them in set notation. All right, let's continue. So here's an interesting function. So it's the function 1 divided by x minus 2. And we called these guys the other day rational functions. And I've given you the graph. I'm going to put little arrows here and here. Maybe you can too on your lesson sheet. So look at the equation, look at the graph. So can you maybe even just focus on the equation? Think about if you were to plug in values for x and do this on your calculator. What x value would give you a problem? Can you see that? Which x value is going to give you a problem in plugging into that function y equals 1 over x minus 2? Can you see what it is? Remember, what number can you not divide by? If you said 2 gives you a problem, you'd be right. Because if we think about it, if you plugged in 2, you would get 1 divided by 2 minus 2, and you get 1 divided by 0, and that's a problem. That gives you an error on your calculator, right? You can't divide by 0. So the domain for this function, I can plug in any x value I want except 2. And the graph shows that too, right? The graph shows you that everywhere has a point except x equals 2. So we'll say for the domain, I'm going to write it in words first. I'll say x can be any real number except 2. Now, how do I write that in set notation? So we'll do it this way. We'll say x can be any real number. There is a restriction here. X can't be 2. So our way of writing that, we just say x equals not 2. So that's how we can handle situations like that, where the x can't be one specific value. Can you see from the graph what y value never happens on this graph? Or think about the equation. There's actually one number that's impossible to get. And if you said that y can't be 0, good for you. Because from the graph, you can see that the graph never touches y equals 0. And if you think about it, the only way to get 0 when you're doing a division is to do 0 divided by a number. And if the top is always 1, you're never going to get 0. So for our range, y can be any real number. We can see that this graph goes forever up and forever down, but it doesn't touch one value. It doesn't touch y equals 0. So we'll say y cannot be 0. And just as an aside, and we'll talk more about this in a later unit, but the values that this function doesn't hit, that vertical line x equals 2 and the horizontal line y equals 0, we give those a special name, and they're called asymptotes. We'll come back to those later, but that's just an interesting aside. It's not really crucial to know right now. All right, let's do another example. So here we have a circle. And again, I don't need you guys to be able to graph a circle. I had a little note here. What the learning was in grade 10 is that equations of this form always give you a circle. The circle always has its center at the origin, 0, 0. And the radius of the circle is always given by, you can always get the radius because the number on the right is always the radius squared. So if the number on the right here is 25, then that means the radius squared is 25, which means the radius of the circle is 5. So that's how we get the graph there. So let's look at this graph. What x values does this graph touch? Does it go forever to the right and forever to the left? Or is it stuck between certain values? And it's actually stuck between certain values. The x values are always between -5 and 5. So how can we write that in math? we do it this way. So we'll say x can be any real number, but it has to be between -5 and 5. And the way that we write that is this. We write the lower number first, -5, less than or equal to sign x, less than or equal to sign 5. So what this is saying is that x is between -5 and 5. And that's the notation we can use to say it's between certain values. Now that we've done the domain, the range is kind of easy because the y values are also stuck between -5 and 5. So we can say for this circle, the y values are between -5 and 5. So y is a real number, but the y value is between -5 and 5. So we've covered a lot of cases. We covered when the number can be anything. Here, between certain values. We covered when it's above a certain value. Let's continue. So this is a radical function, and I've graphed it for you guys here. And if we look at the graph, you can see that the x values are only ever 1 and above 1. And the y values are always 2 or above 2. Why is that? Well, if you plug in a number less than 1 into this equation, you get a negative under the root. And we can't root negatives, that's no good. So that's why the domain for this one, from the equation or from the graph, is x is greater than or equal to 1. Now, we've actually already covered how to handle greater than or equal to, so we can write that out. Maybe I didn't need to write that out, but that's okay. Just in our notes one more time. So x can be any real number, and we say x is greater than or equal to 1. For the range, it's very similar. If we look at the y values of that graph are always greater than or equal to 2. They're never below that. And that makes sense too. If you look at the equation, what kind of numbers come out of a square root? They're always positive, or the lowest they can be is 0. Well, that means that the lowest the entire thing can be is 2, because 0 plus 2 is 2. So a little bit more experience picking off domain and range given a graph. All right, we got 2 more examples. A little heavier lesson today. Definitely some new terminology and maybe some new notation for you as well. But sometimes what we're going to find is that real life can restrict domain and range. It might not be exactly what we think. So let me show you an example of that. So I've constructed a pretty simple quadratic function here from this scenario. I just throwing one of my son's beanbags down the stairs. So something we could all hopefully understand is that when we throw a projectile up in the air, it follows the path of a parabola. So here, I'm throwing Bryden's beanbag off the stairs. It's the path of a parabola, and the equation governing that is -5 times t squared plus 5. And t is in seconds. So I've given you guys a table. Can you plug in those 6 values for t? What values do you get for the height? Plot them on the graph, and we'll talk about the domain and range. So remember, t is actually a real measurement now. It's time. And h is a real measurement too. It's in meters. So you can pause the video and do that and fast forward when you're ready. Or you can just get the y values, the h values here with me. But when you plug in t equals 0, and again, our equation is -5 t squared plus 5. So when you plug in 0, you get 5. That is an awful 5. I'm going to erase that. Pretend that never happened. Plug in 0, you get 5. Hopefully that one's obvious. Maybe I'll show my work for 0.2. So we're just doing -5 times 0.2 squared plus 5. Now, shot a lot of lessons today. So I'm not exactly going to do that using mental math. I'm just going to use my calculator. And I got 4.8. So at this point, again, you can pause the video and just do it and fast forward. I just like to do the math with my students, even if I'm shooting a video. So if you don't want to watch this, that's totally understandable. And then I got 4.2. 5 times 0.6 squared plus 5. I got 3.2. 3.2. And then 1.8. And then you should get 0 for the last one. So if we plot those points, get 0, 5. Just plot them the best you can. 0.2, 4.8, 0.4, 4.2, 0.6, 3.2, 0.8, 1.8, and then 1, 0. Now, let's think about this. Are there any points outside that range we want to graph? Well, time starts with 0, so it doesn't make sense to have negative time. And at t equals 1, what's happening? Well, at t equals 1, the height is 0, so the beanbag has hit the ground. And it's not going to dive under the ground unless it was like, unless the beanbag was like made up of like neutron stars. It's not going to like fly through the staircase. This is it. This is what our graph looks like. It starts at t equals 0. The beanbag falls down, and then it hits the ground at t equals 1, and that's it. There's no other graph. So real life here has restricted our domain and range. Time here only goes between 0 and 1. Starts the throw at 0, beanbag hits the ground at 1. So how can we write that? Well, we would say that time, t, is any real number, and here it's between 0 and 1. We know how to handle that. 0 less than or equal to t, less than or equal to 1. That's how we say that t is between 0 and 1. What's the range? What possible heights above the floor does the beanbag hit? Well, its highest point above the floor is 5 meters, and its lowest point is when it hits the ground at 0 meters. So the range here, we would say, is that the height is a real number, and the height is between 0 and 5. If we think back to the example we had here, so we saw for this parabola, the domain was x can be anything because it's a parabola. You can plug in any number you want. And even though Bryden's beanbag followed the path of a parabola, because we were dealing with time in real life and it hit the ground, that only this part of the parabola makes sense, is relevant. And so that affected our domain and range. All right, guys, we're doing great. Got one more example to do with you. And this example kind of reviews how to make a model of a situation. So here we have what we're going to do is we're enclosing off a rectangular area behind a building. So this is a top-down view of a building. So I've even tried to draw like a nice roof. So you can see this is like you're in the sky, like in a drone looking down. And we want to build a dog run around the outside of the building here. But the thing is, if you're building a fence around a building, you don't need to put fence up. Like, I don't need to put fencing here, right? Like, that'd be dumb because it's like right up against the building. What's the point of that? The building is like its own fence, right? So we're only putting fence around these 3 sides. So what we'd like to do is we're going to come up with a function that models the area of that dog run. And so let's do this. Let's let x be the width. So I'm saying this is the width. Let's say that this length is x. So we could make, x could be pretty small and you can have a really long and narrow one, or x can be like really tall and skinny. Let's say x, and we don't need a different variable for the length, because if we think about it, we've got 100 meters of fencing available. So what's left for the length? Well, the length would be, we have 100 meters of fencing, and for the width, we've used up 2 of the width. right? Think about this. Let's say the width was 10. So you'd have 10 and you'd have 10, and that leaves 80 left over, right? 100 minus 20. So this is an expression for the length of the dog run. So in your grade, maybe a little bit in the grade 9 course, but in your grade 10 course, you do set up problems like this. And taking the grade 11 functions course, it's kind of expected that with a little bit of guidance, you might need help setting up this problem, but you can, once we've established a variable for the width, that we can develop an expression for the width, for the length, and it's not too onerous. Like we can do it. So having seen it at this level, we should be like, okay, that makes sense for the width, for the length. Let's get an expression for the area. So we know that area equals length times width, the area of a rectangle. Well, I have expressions for both of those now, right? So area equals, well, the length is 1,000 minus 2x, and we said the width was x. And that's actually a totally legitimate, and we can see that it actually will turn out to be quadratic. You may prefer to write it like this, though. 1,000 minus 2x. Put or there. So we've done part A. We've expressed, this is what it was asking for. Express the area in terms of the width. Now, we want to determine the domain and range for the area function. So let's go ahead and do that. And I have my next, I'm just going to do that on a separate slide here. So if you remember, if we recall, our expression was x times 100 minus 2x. So I want you guys to think, what kind of lengths are possible for the width of this dog run? Could you have negative lengths? Could the length be 0? Could it be 5? Could it be 50? Could it be 70? You might want to pause and think about this. What's the smallest length possible? And what's the biggest length possible? You can unpause when you're ready or follow along with me right now. So for the width, well, the width has to be, you can't have a negative fence, right? It has to be more than 0. But the highest value the width can be is 50. Because remember, you have a width on this side and a width on this side, and you only have 100 meters of fencing. So if it was more than 50, you'd run out of fencing. So the width is between 0 and 50. Well, we know how to write that. So for the domain, x can be any real number. The width can be any real number between 0 and 50. So 0 less than or equal to x less than or equal to 50. Let's talk about the range. So the range is a little more challenging for, now I will say in your grade 10 course, you guys actually learned that this actually is it turns out to be quadratic. You can sketch it and there's ways to find the maximum. We are going to review those in a few lessons time. For now, what I'll tell you is to get this one, I just used a graphing program, and we're going to do it by hand later, and we will review that. So you don't really need to worry about where this number came from. But for the range, well, I shouldn't say that, is you could go into Desmos, let's say, and plug in this function, and it would give you the range. So the area has a maximum of 1,250 meters squared, and the lowest an area would be 0. So for the range, we would say the area can be any real number, and the area is between 0 and 1,250. And you know what? I'm going to call an audible here, and I'm just going to show you guys how we could do this. So I'm going to exit out here. I'm going to keep those for later. I'm going to be using my graphing program. And we're just going to graph this one. So just bear with me for a second. I'm going to insert my function. And my function was x times 100 minus 2x. And I'm going to do it from 0 to 50 because that was my domain. And you'll notice the x times 200 minus 2x. Okay, so you notice I didn't really get a graph. That's because I need to change my axis. So I'm going to do that. I'm going to change this from maybe -5 to 50. Intervals of 5. And go from -100 to say 1400, ticks of 100, grid units of 50. That should be, yeah, this is good. So when we graph this relation, so I've used my graphing program. Desmos or other graphing programs can do just as good of a job. But you can see this graph is a parabola. You can see it goes between 0 and 50 before the area goes negative. And the absolute highest you get, you can see, is halfway between 1200 and 1300. It's 1250. So we will review how to find that by hand. But right now, you could just use a graphing program. Right now, the intention is just to talk about domain and range like from a graph. So I'm going to head back into my PowerPoint and finish off this lesson with you guys. All right, so we finished up that last real life example. What do I really need you guys to be able to do after this lesson? I need you guys to know what domain and range is. And if you can identify the domain and range of a function by looking at the graph, you're in good shape. We'd like to move towards being able to see right from the equation what the domain and range is. But if you can identify it from the graph, you're doing good. And you may have to get used to the new notation if you haven't used it before. But I will tell you that I have practice and activities for you guys to do. Like if you're taking the class right now, if you're just some random person on YouTube learning what domain and range, hello, but I don't have the practice for you. But in our next lesson, we're going to learn some new notation. Because if I want to describe the output I get, so when I say like I put in an x value of 2, what y value do I get? Instead of saying the y value in x equals 2, that's kind of a mouthful. It's a little bit inefficient. We're going to introduce some new notation that is essential for not just this course, but in every single math course you take in the future. So if you're eyeing up calculus in grade 12, if you're going to university in the sciences or math or engineering, you will be using this notation and it's crucial. And so we're going to introduce it in our next lesson. But for now, practice your domain and range stuff, guys. Hope you're staying well. Have a great day and we'll see you soon.